A field hospital behind the Eastern Front. The winter of 1943. A German infantryman lies on a canvas cot, and he is dying of something that should not be able to kill him. Days earlier, a fragment of shell casing had opened a wound in his thigh. It was not, by the standards of that front, a serious injury. The surgeons had cleaned it, dusted it with sulfur powder, and moved on to the men who were bleeding out. But the wound has turned. The skin around it has gone dusky and tight. There is a faint crackling under the surgeon's fingers when he presses, the signature of gas forming in the tissue, and there is a sweetish odor that every experienced field surgeon on that front has learned to dread. This is gas gangrene, an infection that races through injured muscle faster than a scalpel can chase it. The surgeon does what German doctrine allows him to do. He gives more sulfonamide. He opens the wound wider and cuts away the dead tissue. When that fails, he prepares to take the leg. And when that fails too, because the infection is already in the blood, he steps back, because there is nothing left in the German medical kit that can reach into this man's body and kill the bacteria multiplying inside him. The soldier's fever climbs, his breathing shortens. Sometime in the night he stops. This scene, in one form or another, repeated itself across thousands of German field hospitals throughout the war. Now hold that scene in your mind, because there is a second scene happening at the very same moment, a few hundred miles to the west, in an Allied field hospital. There a soldier lies with a wound almost identical to the Germans. Same torn muscle, same invading bacteria, same race between infection and death. But this man receives something the German did not. Every few hours, an orderly injects a pale yellow fluid into his arm. Within a day, the redness recedes. Within a week, the fever is gone. He keeps his leg. He keeps his life. The fluid is penicillin, and by the winter of 1943, the Allies are making it by the trillions of units, while Germany is making almost none. Here is what makes those two scenes a genuine puzzle, rather than simply a tragedy. The German soldier did not die because German medicine was primitive. He died inside the most scientifically advanced medical culture on Earth. Germany had, for 2 generations, led the world in chemistry, in pharmacology, in the industrial manufacture of medicines. The very idea of a drug that could be swallowed or injected to cure an infection from the inside, the whole concept of chemical therapy against bacteria, had been born in German laboratories. The sulfur powder the surgeon sprinkled into that wound was itself a German invention, and a Nobel Prize-winning one. If any nation on the planet should have been able to hand its wounded soldiers the newest miracle drug against infection, it was Germany. And yet it was the one thing Germany could not do. This is a strange thing to find in the intelligence record, but it is there. When Allied investigators went through captured German laboratories and interrogated German scientists after the war, they kept arriving at the same conclusion, phrased slightly differently in report after report. The Germans had understood penicillin. They had read the science. They had grasped exactly what it was and exactly how valuable it would be. And they had been unable to make it in any quantity that mattered. They knew what it was. They simply could not make it. That sentence, in one form or another, runs through the whole German story like a thread. So the question this account exists to answer is not why penicillin worked. It worked identically for everyone. The molecule did not care which uniform a man wore. The question is why the same drug, discovered from the same mold, understood by the scientists of both sides, existed in oceans on one side of the line and in thimbles on the other. Why could the United States, which before the war had barely any presence in this field at all, flood its hospitals with penicillin, while Germany, the birthplace of modern pharmaceutical chemistry, watched its own wounded die of infections it knew perfectly well how to cure in principle and could not cure in practice? The obvious answers are the ones to be suspicious of. It is tempting to say that Allied bombing simply flattened the German factories, and bombing certainly hurt. It is tempting to say the Germans started too late, and they did start late. It is tempting to say the Germans were cut off from the crucial mold strains and the published methods, and there is truth in that too. But none of these is the real answer, because each of them describes a symptom rather than the disease. the deeper reason has almost nothing to do with the war itself. It reaches back 2 decades and more before the first shot, to a difference in how two scientific cultures thought about the most basic question of all. What kind of problem is penicillin? Is it a problem of chemistry, something you conquer by understanding a molecule and building it atom by atom? Or is it a problem of biology, something you solve not by understanding it fully, but by coaxing a living thing to do the work for you? Germany answered that question one way. The Americans answered it the other way. And the man dying on that cot was, without ever knowing it, a casualty of the answer his own country had chosen. To understand why the German answer was so seductive, and why it was also a trap, you have to take German medical science seriously, because it was genuinely magnificent. For most of the 19th and early 20th centuries, if you wanted to study medicine or chemistry at the highest level, you learned German and you went to Germany. German universities and German industry had fused chemistry and medicine into something the world had never seen. The great dye companies, firms that had grown rich turning coal tar into brilliant fabric colors, discovered that the same chemical skills that produced dyes could produce drugs. These companies eventually merged into a single colossus, the chemical combine known as IG Farben, which by the 1930s was arguably the most powerful industrial research organization on the planet. Inside it worked chemists who could look at a molecule, take it apart in their minds, and build a new one to order. The founding hero of this whole tradition was a German scientist named Paul Ehrlich, and his story explains the mindset perfectly. Around the turn of the century, Ehrlich imagined something he called a magic bullet, a chemical that could travel through the body and strike only the invading germ while leaving the patient unharmed. He did not wait for nature to hand him such a thing. He set his laboratory to synthesizing and testing hundreds of arsenic-based compounds, one after another, searching for the one that would work. In 1910 he found it, a compound effective against the organism that causes syphilis, which he marketed under the name Salvarsan. It was the first time in history that a disease had been defeated by a chemical designed and built for the purpose. Ehrlich even gave the whole approach its name. He called it chemotherapy. This was the German dream in its purest form, mastery through synthesis. You do not stumble onto a cure. You reason your way to the molecule you need, and you build it. Every triumph of German pharmaceutical science for the next 30 years flowed from that conviction, and every one of those triumphs made the conviction stronger. By the outbreak of the war, this tradition had produced an almost unbroken run of victories. German laboratories had given the world aspirin and a long roll of other medicines. German chemists had unraveled the structures of natural substances that had baffled everyone before them. German firms held the patents, German journals set the standards, and ambitious young scientists from every country still crossed borders to train in German institutes. The country's faith in the synthetic method was not mere arrogance. It was the reasonable conclusion drawn from decades of being right. When you have solved problem after problem by understanding a molecule and then building it, you naturally assume the next problem will yield to the same approach. Penicillin looked like simply one more molecule waiting to be understood and constructed. The assumption was wrong, but it was wrong for reasons that no amount of German brilliance could easily have foreseen, and that is exactly what made the trap so difficult to escape. Out of exactly this tradition came the drug that seemed to make penicillin unnecessary. In the early 1930s, a physician and researcher named Gerhard Domach, working in the laboratories of that German chemical empire, was systematically testing synthetic dyes to see whether any of them could kill bacteria inside a living animal. In 1932, he found one. A reddish compound, later marketed under the name Prontosil, protected mice from lethal doses of streptococcus. It was the first substance in history that could be given to a patient to cure a raging bacterial infection from within. Domach had been driven to this search by memory. As a young medical orderly in the previous World War, he had watched countless wounded men die of infections that no surgeon could stop, and gas gangrene in particular had haunted him. Now he had found a weapon against exactly that helplessness. He proved it in the most personal way imaginable. When his own young daughter developed a severe infection from a needle wound, an infection so bad that doctors were preparing to amputate her arm, he treated her with his experimental compound and she recovered completely, arm and all. For this work, Domark was awarded the Nobel Prize in 1939, an honor the Nazi regime forced him to refuse at the time, and which he was only able to accept years later, in 1947. Understand what this meant psychologically for German medicine. Germany had built the entire modern idea of curing infection with chemistry, and now Germany had produced the first practical drug that did it. The sulfur drugs that grew out of Domark's discovery spread across the world in the late 1930s. They were carried in the medical kits of armies everywhere, including, soon, the American and British armies. They cured pneumonia, wound infections, and childbed fever that had killed people for all of human history. The son of a sitting American president was famously cured by one of them. A British prime minister would later be treated with them as well. They were a triumph of exactly the German approach, the approach of the master chemist who understands a molecule and synthesizes it in a factory. So when whispers of a strange new mold juice called penicillin began to circulate, the German establishment had every reason to be skeptical. Why chase after some finicky substance dripped from a fungus when Germany already held the crown, when Germany already had a family of proven, patentable, factory-made drugs that did the same job? The very success of German chemistry made penicillin look like a step backward, a return to brewing and farming when the future was supposed to belong to the laboratory. If you find this kind of history worth telling, the forgotten reasons behind who lived and who died, please consider subscribing and leaving a like. It genuinely helps this sort of detailed account reach more people who care about getting the story right. Now let us be clear about what the sulfur drugs could and could not do, because this is where the human stakes come sharply into focus. Sulfonamides were a real advance, but they were a limited one. They slowed bacteria rather than reliably killing them outright, and they worked well against some infections and poorly against others. They came with genuine side effects, and they demanded that the patient's own body finish the job the drug had only started. Crucially, they were weak against precisely the kind of deep, dirty, oxygen-starved wound infections that dominated the battlefield, including gas gangrene, the very thing that killed the soldier we began with. Penicillin was different in degree and almost in kind. It was dramatically more powerful, it reached infections sulfur could not touch, and it did so with far less toxicity to the patient. The gap between the two drugs was not a matter of a few percentage points. It was the difference between a wound that killed a man and the same wound that inconvenienced him for a fortnight. The numbers that came out of the war make the gap brutally concrete. In the earlier World War, before either drug existed, infections had been among the great killers of soldiers. Pneumonia alone killed something close to a quarter of the American soldiers who developed it. Gas gangrene turned minor wounds into death sentences at a horrifying rate. For most of the history of warfare, a great many of the men who died of their wounds were killed not by the wound itself, but by the infection that set in afterward. By the later years of the Second War, among Allied troops with access to penicillin, the picture had transformed. Deaths from bacterial pneumonia fell to a tiny fraction of what they had been, well under 1 in 100 cases. And here is the comparison that says everything. Among Allied troops treated in the penicillin era, gas gangrene occurred in roughly 1.5 cases per 1,000 wounded. Among German prisoners of war, who in the main were still being treated with sulfur drugs because that was what Germany had, gangrene ran at something like 20 to 30 cases per 1,000. Same infection, same human bodies, two entirely different survival curves, separated by which drug a man's army could put in his veins. The soldier on the German cot was not an unlucky exception. He was the statistical rule for a nation fighting the infection war with the previous generation's weapon. It is hard, from the vantage of the present, to feel how total that helplessness had once been. For almost all of human history until the 1930s, there was essentially nothing a doctor could do once bacteria got into the blood. A scratch from a garden thorn, a blister rubbed raw on a long march, a scrape from a strand of rusty wire. Any of these could seed an infection that spread inward and killed a healthy adult within days. And the finest physician in the world could only stand at the bedside and watch it happen. Surgeons cut in the grim knowledge that the operation itself might introduce the infection that finished the patient. Mothers died of fevers in their own clean beds in the days after giving birth. This was the ancient condition that Dommark's sulfur drugs had cracked open for the very first time, and it was the same condition that penicillin, far more powerfully, promised to end altogether. That is why the stakes were so enormous. A nation that could make penicillin in abundance held something close to a superpower over a nation that could not, because the wounded man's chance of survival now depended less on the skill of his surgeon than on the output of his country's fermentation tanks. The bitter irony is that Germany's helplessness flowed directly out of Germany's strength. The same national pride in chemistry that had produced the sulfur triumph became the reason Germany could not pivot to penicillin, and the man who embodied that pride made the fateful recommendation himself. Gerhard Dommark, the father of the sulfur drugs, is reported to have advised the German government to concentrate on improving his own class of drugs rather than pouring resources into chasing penicillin. From inside the German worldview, this was not foolish. It was the confident judgment of the world's leading expert, who believed, understandably, that the future lay with the synthetic molecule he understood and could refine, not with a temperamental mold that no one in Germany yet knew how to tame. German research on penicillin did not begin in earnest until 1942, and even then, it was scattered and starved of resources. It was not until the end of 1943, prompted in part by the hard experience of the fighting in North Africa, that the German authorities formally recognized how badly they needed penicillin of their own and ordered a real effort. The Reich Health Ministry issued that order only in December of 1943. By then, the Americans were already producing penicillin in industrial quantities. It is worth pausing on just how much the Germans did know, because it destroys any notion that this was a failure of intelligence or information. German scientists had read the Oxford team's published work. In the summer of 1943, a German pharmacologist in Berlin published a survey of the international literature on these new antibacterial substances that included the British penicillin papers, laying the science out plainly for any German researcher who cared to look. German firms obtained samples of the Penicillium mold from a culture collection in the German-occupied Netherlands. When the Afrika Korps captured Allied medical supplies in North Africa, vials of actual penicillin were sent back to Germany for study, and one of them reached the chemical firm Höchst. The Berlin firm Schering tried to grow Fleming's mold and tried to work out the drug's chemical structure, and failed at both. So the German scientists were not fumbling in the dark. They had the papers, they had the mold, and they even had physical samples of the finished drug in their hands. What they could not do was turn any of that into a manufacturing process that produced meaningful quantities. They knew what penicillin was, they could not make it. Both halves stayed true no matter how much knowledge they accumulated. There is something close to tragedy in the position of those German researchers, and it deserves to be said plainly, because they were not fools and they were not idle. They were capable scientists watching, from the inside, as their own country failed to make a drug they knew perfectly well could save their wounded countrymen. They wrote up what they could learn. They asked for materials and mold strains they were never able to get. They worked in laboratories that grew more likely to be bombed with every passing month, on budgets that would have embarrassed a single American university department, with no one above them able to knit their scattered efforts into a coherent whole. When Allied officers questioned them after the surrender, the frustration comes through even in the dry official language of the reports. These men had seen the future of medicine clearly. They had simply been unable to reach it with the tools their nation had chosen to bring to the fight. And when German scientists finally did commit to the problem, they ran straight into the wall that their entire scientific culture had built for them. They approached penicillin the way Ehrlich would have, the way they approached everything, as a chemistry problem. The instinct of the great German pharmaceutical tradition was to isolate the molecule, determine its exact structure, and then synthesize it, build it up from simpler chemicals in a reaction vessel under precise control. This was the German way, the elegant way, the way that had conquered dye after dye and drug after drug. But penicillin refused to yield to it. The penicillin molecule turned out to contain a fiendishly unstable internal structure, a strained ring of atoms that fell apart under almost every chemical manipulation chemists tried to use on it. The molecule was small, its weight was well within the range of things chemists had built before, and yet it defeated them, because the specific techniques needed to assemble that fragile ring simply did not yet exist anywhere in the world. The German effort to nail down the structure and synthesize the drug stalled, as indeed the parallel Allied effort to synthesize it also stalled. On this narrow point, the Germans were not uniquely failing. Nobody on Earth could synthesize penicillin during the war. The difference was that the Americans had stopped waiting for chemistry to solve the problem, and Germany, culturally, could not stop waiting. Because here is the pivot, and it happens far from any battlefield, in a place that could not sound less like the center of a wartime revolution. To find the reason the Allies drowned in penicillin while Germany went dry, you have to leave the laboratories of the great chemical empires entirely and travel to a modest government research station on the edge of a small city in the American Midwest, Peoria, Illinois. There, the United States Department of Agriculture ran a laboratory called the Northern Regional Research Laboratory, a place whose entire reason for existing was deeply unglamorous. Its job was to find useful things to do with the surplus crops of American farmers, how to turn mountains of corn and wheat and agricultural waste into something valuable. The scientists there were experts in fermentation, in the industrial art of getting molds and microbes to eat cheap raw materials and produce useful substances. This was not prestigious science. It was, in the hierarchy of the scientific world in 1941, close to the bottom, and it was about to become the most important laboratory in the history of medicine. It is worth asking why this expertise existed in America at all, and in a government farm laboratory of all places. The answer lies in something as ordinary as surplus crops. American farms produced staggering quantities of corn and other grains, far more than the market could absorb, and for decades, scientists had been paid to find industrial uses for the excess, ways to turn cheap agricultural material into valuable products through fermentation. That meant America had quietly built up, in places nobody thought about, a deep practical knowledge of how to grow molds and microbes in bulk, how to feed them, how to keep them healthy, and how to harvest what they made. It was humble, unfashionable work with no glamour and little prestige attached to it, and it happened to be the exact body of skill that the penicillin problem would demand. Germany, with its smaller agriculture and its prestige invested in synthetic chemistry, had never built anything comparable. The knowledge that would go on to save so many Allied lives had been accumulating, entirely unnoticed, in one of the least likely corners of American science. To see how Peoria entered the story, we have to back up to where penicillin actually came from, because the discovery was not American at all. It was British, and it had been sitting almost useless for over a decade. In 1928, at St. Mary's Hospital in London, a bacteriologist named Alexander Fleming returned from holiday to find that a mold had drifted into one of his bacterial culture dishes and killed the bacteria around it. He identified the mold, named the substance it produced penicillin, published his observation in 1929, and then, essentially, could take it no further. Fleming was not a chemist, and the substance was maddeningly difficult to extract and keep stable. For roughly 10 years, penicillin remained a laboratory curiosity, a note in a journal, interesting and useless. It is worth understanding why it sat unused for so long, because the reason is the whole story in miniature. Penicillin, as it seeps from the mold, is present only in tiny amounts and is extraordinarily delicate. Try to concentrate it and it falls apart. Shift its acidity slightly and it dies. Fleming's own assistants attempted to purify it and could not hold on to it. Other researchers picked it up over the following decade and set it down again, defeated by the same fragility. Fleming himself came to think it might be useful mainly as a laboratory tool for separating one kind of bacteria from another, rather than as a medicine at all. The substance was real, and its power against bacteria was plain under the microscope, but turning that flicker of promise into something you could put in a bottle and inject into a dying man seemed, for 10 long years, simply beyond reach. The problem was never whether penicillin worked. The problem, from the very first day, was making enough of it, and making it pure. Everything that followed was one long war against that single obstacle. What rescued it was a team at Oxford at the end of the 1930s. Led by a hard-driving Australian pathologist named Howard Florey, and including the brilliant biochemist Ernst Chain, who was himself a refugee who had fled Germany, and a quietly ingenious biochemist named Norman Heatley, the Oxford group set out to turn Fleming's curiosity into an actual medicine. They succeeded in extracting enough purified penicillin to test it, and in 1940 they showed that it could save mice deliberately infected with lethal bacteria. Then, in February of 1941, they tried it on a human being for the first time, a policeman from near Oxford who was gravely ill with a spreading infection. The effect was miraculous at first. The man began to recover, and then the penicillin ran out. The Oxford team was reduced to recovering the drug from the patient's own urine to purify and reuse it, and even that was not enough. The supply failed, and the patient died. That single case captured the entire problem in miniature. The drug worked. There was simply no way to make enough of it. Producing penicillin in Fleming's, and even in Oxford's fashion, meant growing the mold on the surface of countless small vessels, in flasks and bottles, and, famously, in repurposed hospital bedpans, each one yielding only a trace of the precious substance. Oxford even hired a team of young women, remembered later as the Penicillin Girls, paid a couple of pounds a week to tend this sprawling mold farm. To treat one patient took the output of hundreds of these vessels. To treat an army was unthinkable. The night of the team's first real animal experiment is remembered in the history of medicine. They had infected 8 mice with a dose of bacteria that should have killed all of them, and given 4 of the 8 penicillin. Through the night, one of the researchers stayed to watch as the 4 treated mice remained alive and well, while the 4 untreated ones sickened and died. By morning, the result was beyond argument. A member of the team is said to have called it a miracle. They understood at once that they were looking at something that could save an almost unimaginable number of human lives, if, and it was an enormous if, anyone on Earth could ever make it in quantity. Everything the Oxford group did afterward, all the bedpans and improvised vessels and painstaking extraction by hand, was an attempt to climb that mountain with the resources of a single university department in a country fighting for its survival. It was never going to be enough. The scale the problem demanded belonged to industry, and industry on that scale belonged, in 1941, to only one great power left standing outside the reach of the bombs. The Oxford scientists understood that Britain, fighting for its life and being bombed nightly, did not have the industrial capacity to solve this. So in the summer of 1941, Florey and Heatley crossed the Atlantic to ask the Americans for help. Through a chain of contacts, including an American mycologist who knew exactly where the right expertise lived, they were directed to that unglamorous fermentation laboratory in Peoria. They arrived in July of 1941. The laboratory's director and the head of its fermentation division threw the institution's weight behind the problem at once, and Heatley stayed on for months, working side by side with an American mold specialist to push the yields up. This is the moment the whole history turns, because the Peoria scientists looked at penicillin and did not see the problem the chemists saw. They did not see a molecule to be understood and synthesized. They saw a mold that needed to be persuaded to grow better and produce more. To the fermentation experts of the American Midwest, penicillin was not a chemistry problem at all. It was a farming problem, and farming was exactly what they knew how to do. This is the hidden insight at the heart of the entire story, and it is worth stating as plainly as possible. The Germans, and the great chemical tradition they represented, believed that to truly command a drug, you had to understand it and build it. Control meant synthesis. Anything less, Growing it in vats of mold like beer or cheese felt like a primitive detour, a temporary embarrassment to be replaced as soon as the chemists cracked the structure. The Americans in Peoria made the opposite bet. They decided they did not need to understand penicillin fully or build it at all. They needed only to get a living organism to make it for them, in staggering quantity, at industrial scale. They would not conquer the molecule, they would harness the mold. That single difference in philosophy, understanding versus harnessing, chemistry versus biology, is the reason one side had penicillin and the other did not. Once you make that decision, the problem transforms into a series of practical questions that fermentation experts are perfectly equipped to attack. And the Peoria laboratory attacked them one after another, producing a run of breakthroughs that together turned penicillin from a trickle into a flood. Each one was mundane on its own. Together they changed the world. The first breakthrough was food for the mold. The Oxford recipe grew the mold in a fairly thin nutrient broth. A researcher at Peoria named Andrew Moyer began experimenting with what he fed the fungus, and he had a peculiar resource close at hand. The corn processing industry of the American Midwest produced enormous quantities of a thick, sour byproduct called corn steep liquor, a leftover from the wet milling of corn that was so unwanted it was often simply poured into the river. Moyer tried adding this waste liquid to the mold's diet. The effect was dramatic. The mold, fed on this cheap industrial leftover, produced many times more penicillin than before, something on the order of a 10-fold increase. A waste product that American industry had literally been throwing away turned out to be the ideal fuel for manufacturing the most valuable medicine on Earth. No German laboratory had this particular resource sitting in a barrel outside the door, and no purely chemical approach would ever have thought to look for it. It was the kind of solution that only a culture steeped in agricultural fermentation would even go searching for. The second breakthrough was even more fundamental, and it was a question of geometry. Growing the mold on the surface of shallow trays and bottles was hopelessly inefficient, because the mold only grew where it met the air. If you wanted more penicillin, you needed more surface, which meant more and more vessels, endlessly. The dream was to grow the mold not on the surface but throughout the entire depth of a huge tank of liquid, suspended in the broth, fed with air bubbled continuously through it, so the whole volume became productive at once. This is called submerged deep tank fermentation, and it is easy to describe and brutally hard to do. The mold strains that grew beautifully on the surface often refused to perform when plunged into a churning tank, so new strains had to be selected specifically for life in the deep. Air blown into the tank had to be perfectly sterile, because a single stray contaminating microbe could spoil thousands of gallons overnight. The nutrient broth, rich with corn steep liquor, foamed violently when air was forced through it, and that foaming had to be tamed with special agents before it swamped the whole operation. The liquid had to be constantly stirred and cooled and held at exactly the right conditions. Enormous tanks had to be kept as clean as a surgical instrument for days on end. This was not the chemistry of the reaction vessel. This was the biology of the brewery and the engineering of the factory, married together at a scale never before attempted for a living organism grown to make medicine. And here a second unglamorous piece of American industrial history clicks into place, because one company was almost uniquely prepared to solve exactly this problem. The Brooklyn firm of Pfizer had spent years before the war mastering the art of large-scale fermentation, not for medicine, but for a humble product. Citric acid, the sour flavoring used in soft drinks and foods, which Pfizer had learned to produce by fermenting sugar with mold in large vessels. A chemist at Pfizer named Jasper Kane, who understood this fermentation art intimately, proposed that the company gamble on producing penicillin by the deep tank method. It was a genuine gamble, and the company's leadership knew it. One senior figure famously warned that the mold was as temperamental as an opera singer, that the yields were low, the isolation difficult, the extraction murderous, and the purification an invitation to disaster. But Pfizer committed anyway. The company bought an old ice plant in Brooklyn and converted it, drawing on the talent of pioneering engineers, among them a chemical engineer named Margaret Hutchinson Rousseau, who helped design the first plant of its kind. Pfizer built the facility around a bank of 14 deep tanks, each holding 7,500 gallons. When it opened in the spring of 1944, that single plant could produce more penicillin in a month than the entire country had made in all of the previous year. Years of quiet expertise in making flavoring sour had, by an accident of history, positioned an American company to manufacture the miracle drug of the century. The third breakthrough came from a worldwide hunt for a better mold. Fleming's original strain was a poor producer, and the Peoria scientists knew that somewhere in nature there might be a wild cousin that produced far more. They put out a call for moldy samples from around the world, and soldiers and pilots and ordinary citizens sent in rotting fruit and moldy soil from wherever they happened to be. Researchers screened strain after strain looking for a champion. In one of the most quietly famous episodes in the history of medicine, the winner was found close to home, on a moldy cantaloupe from a fruit market in Peoria itself. The mold growing on that melon, a species called Penicillium chrysogenum, turned out to be an extraordinary producer, and the strain isolated from it became the ancestor of essentially all the penicillin manufactured for the rest of the war and long afterward. The scientists then pushed it even further, bombarding the mold with X-rays at one research institution and with ultraviolet light at a university laboratory, deliberately triggering mutations and then selecting the mutant offspring that produced still more penicillin. They were breeding a super-productive strain the way a farmer breeds a prize animal over generations. This too was biology, not chemistry. It was the logic of the farm, and the breeder applied to a microbe, and it multiplied the yields again. Taken together, the better food, the better vessel, and the better, mutated strain lifted the amount of penicillin that could be drawn from a single batch to hundreds of times what Fleming's original mold had ever produced on its own. It was one of the most dramatic feats of applied biology ever accomplished, and almost none of the public would ever hear the names of the quiet men and women who did it. None of these three advances, the corn steep liquor, the deep tanks, the champion mold, was a chemical conquest of the penicillin molecule. Every one of them was a way of getting a living thing to work harder and at greater scale. And crucially, none of the people who built these pieces had originally set out to win a war or to defeat German medicine. The Peoria laboratory existed to help farmers. Pfizer's fermentation skill had been built to make food flavoring. The mold hunters were agricultural scientists. Three separate streams of unglamorous, unfashionable American expertise, none of them created for this purpose, all of them converging by chance on the same problem at the same moment, and together solving the thing that the world's proudest chemical establishment could not. What turned this convergence into a torrent was the way the American government harnessed it, and this is the final ingredient the Germans never assembled. It may be the most decisive of all. In the United States, the effort was pulled together and driven forward by a central coordinating power. A federal body, the Committee on Medical Research within the Office of Scientific Research and Development, took charge, championed by a determined administrator named Alfred Newton Richards, who used the authority and trust of the government to force fierce commercial rivals to cooperate. As early as the autumn of 1941, he had gathered the major drug firms and pressed them to treat penicillin as a shared national mission rather than a private race. Companies that would normally guard every secret from one another, Pfizer and Merck and Squibb and Lederle and Abbott and others, were brought together and made to share their methods and their data for the common goal. The government even shielded them from the antitrust laws that would ordinarily have punished such cooperation. When one industrialist was persuaded that the fermentation results were real, he reportedly declared that if the numbers held up, industry would find a way to do it. Then, as the drug's value to the war became undeniable, the War Production Board took direct control. It investigated more than 175 companies, selected 21 of them to manufacture penicillin, and gave them top priority for scarce materials and equipment. Factory workers were told, in slogans posted on the walls and slipped into their pay envelopes, that the penicillin they made today would save a dying man in a matter of days. An entire nation's industrial and scientific machine was pointed at a single goal and coordinated from the top. The scale of that coordination went right down to how the first precious doses were rationed among the sick. In the earliest days, when American penicillin was still measured in tiny amounts, a single physician was appointed to decide who among the desperately ill would receive it, because there was so little to go around. The very first American civilian whose life was saved by it shows how scarce it was. In March of 1942, a young woman in a Connecticut hospital lay dying of a raging blood infection following a miscarriage. Her fever had run wild for weeks, and the doctors expected her to die. They obtained a small quantity of penicillin, at that point about half of the entire supply that existed in the whole country, and injected it. Overnight, her fever broke. Within days, she was sitting up, eating, out of danger. She went on to live for more than half a century afterward. That was what the drug could do, one patient at a time, when there was almost none of it. The whole point of the American machine was to take that miracle and multiply it until it was available not to one dying woman, but to every wounded soldier on a continent. Army trials in 1943, treating hundreds of surgical and wound cases, convinced the military beyond any doubt that this was a weapon worth any industrial price, and the army began consuming the overwhelming majority of everything the country produced. For a stretch of 1943, the rationing of the small civilian supply fell to a single physician, who sat with the pleading requests that poured in from doctors all across the country, each one describing a patient who would surely die without the drug, and who had to decide which few of them could be saved with the tiny amounts on hand. It was an almost unbearable responsibility, and it existed for one reason only, that the supply had not yet caught up with the need. The entire national effort was aimed at making that terrible arithmetic disappear, at reaching the day when no doctor would have to choose, when there would be enough penicillin for every soldier, and, in time, every citizen who needed it. Germany never once faced a choice that agonizing, for a bleak reason of its own. It never had enough penicillin to save even the soldiers at the front, let alone civilians at home, so there was never a surplus over which anyone had to agonize. Now set the German effort beside that, and the contrast is total. Germany never created any equivalent central authority for penicillin. There was no single figure with the power to command the resources of the state, force the great companies to pool their knowledge, and drive the whole thing forward from the top. The effort was fragmented across separate institutions that duplicated each other's work and competed rather than combined. The funding was pitiful by comparison. One of Germany's leading researchers in this area was reportedly working with a research budget of around 25,000 Reichsmarks, roughly $10,000, for the study of these antibacterial compounds, at a moment when the Americans were pouring the equivalent of tens of millions of dollars and the coordinated might of an entire industry into the same problem. Where the Americans had a system, the Germans had scattered individuals doing their best in isolation, and what the German researchers managed to build reflected that. The chemical firm Hoechst, working under one of its researchers, achieved penicillin production only in batches of about 300 liters, a scale that was experimental, where the American tanks were industrial. Even that modest effort was reached only in the autumn of 1944, and Allied bombing then crippled it. By the time of the Normandy invasion in June of 1944, the best German industry could manage was enough crude penicillin to use as a dusting powder on surface wounds. Injectable penicillin, of the kind that saved the Allied soldier's leg, barely existed in German hands at all. Meanwhile, the American output climbed a curve that has few equals in industrial history. Production in the United States went from 21 billion units in 1943 to more than 1.5 trillion units in 1944, to more than 6.8 trillion units in 1945. By the middle of 1944, a single company, Pfizer, was producing on the order of 70 billion units of penicillin every single month. The manufacturing techniques had leaped from 1-liter flasks, yielding a trace of drug, to 10,000-gallon tanks, running at high efficiency. The price collapsed accordingly, from around $20 per 100,000 units early on to a matter of pennies, as the process became routine. Enough penicillin was stockpiled to accompany the Allied armies onto the beaches of Normandy, and most of the penicillin that went ashore in that invasion came from that converted ice plant in Brooklyn. A drug that 3 years earlier had to be recovered from a dying patient's urine because a single dose was too precious to waste, was now being manufactured in quantities large enough to treat every serious casualty of the largest amphibious invasion ever attempted. By the spring of 1945, the American government was able to lift the restrictions entirely, and penicillin appeared on the shelves of ordinary pharmacies for any citizen to buy. By the time of the Normandy landings, the drug had become a fixture of Allied battlefield medicine, carried forward with the advancing armies, and given to a wounded man in a field hospital within hours of his being hit. Its effect reached well beyond torn flesh. Penicillin proved strikingly effective against the venereal infections that had always drained armies of manpower, curing in a few days conditions that had once sidelined soldiers for weeks and returning them to their units almost at once. It cut through pneumonia, through the infections that followed burns and surgery, through the sepsis that had forever been the field surgeon's oldest enemy. It traveled to every theater of the war, from the hedgerows of France to the islands of the Pacific, where wounds fouled quickly in the heat and infection had always been especially deadly. Men who a few years earlier would have died, or would have lived only after losing a limb, now recovered, and in many cases walked back to duty. And there was a quieter effect that was its own kind of weapon. A soldier who believes that a serious wound is very likely a death sentence fights differently from a soldier who believes that if he can only reach a hospital, he will probably live. Penicillin handed the second belief to one side of the war and withheld it from the other. If this account is giving you a new way of seeing that war, a like helps it reach more viewers, and subscribing means the next one of these will find its way to you. Now return, with all of this understood, to the German soldier dying on his cot, and to the puzzle of the intelligence reports, because it resolves completely. His country's scientists had read the same journals as the Oxford team. They had held the same mold, and even captured samples of the finished drug. They understood the penicillin molecule as well as anyone alive. Their chemists were the equals of any in the world. What they lacked was not knowledge and not intelligence. What they lacked was an entire way of thinking about the problem, and the industrial machine that flowed from that way of thinking. They kept trying to conquer penicillin as chemists, to understand it and build it, because that was the German path to glory, and it had never failed them before. The Americans, unburdened by that pride, and rich in exactly the humble fermentation skills that Germany had never bothered to prize, simply grew it. The German field surgeon reaching for sulfur powder was not failed by his own hands or his own training. He was failed by a national scientific culture that had bet everything on the reaction vessel and had nothing to put in his kit when the answer turned out to lie in a vat of mold. German commanders in the field, Erwin Rommel among them, had already come face to face with the wider version of what was happening to their army, the way the Americans could bring overwhelming, systematized industrial power to bear in ways Germany could not match. Penicillin was that same story told in a hospital instead of on a battlefield. It was not that any single American was smarter than any single German. It was that the Americans had built a system running from a cornfield through a fermentation tank to a soldier's vein, and the Germans had built a collection of brilliant individuals who were never assembled into a system at all. And then comes the final turn, the one that seals the whole argument and reveals just how deep the German trap really was. The German dream, the thing they were implicitly waiting for, was to master penicillin properly, to determine its structure and synthesize it in the factory, the way Ehrlich and Dommark had built their drugs. Surely, the thinking went, the crude business of growing mold was a temporary phase, and the real prize would go to whoever first built the molecule by pure chemistry. So it is worth knowing how that race actually ended. The wartime effort to synthesize penicillin by chemistry was itself enormous. On the Allied side alone, something like 1,000 chemists across dozens of laboratories in the United States and Britain, spending roughly $20 million, threw themselves at the problem of building the penicillin molecule from scratch. They failed. The molecule's fragile ring defeated the best chemists in the world. The man who eventually did solve it, years later, described the task, using the methods available at the time, as being like trying to set a heavy anvil down gently on top of a house of cards. The very ring of atoms that gave penicillin its bacteria-killing power was the same ring that collapsed the instant a chemist tried to build it, or even to hold it by the ordinary means of the day. The right tools had not yet been invented. When the war ended, the structure had been worked out, but a practical synthesis had not, and the funding for the chemical assault dried up. The first true chemical synthesis of penicillin was not achieved during the war at all, nor anywhere in the 1940s. It came only in 1957, more than a decade after the fighting stopped, accomplished by a chemist named John Sheehan at the Massachusetts Institute of Technology after 9 years of solitary, painstaking work. And even his triumphant synthesis was far too slow and too costly to compete with mold in a tank. To this day, the world still makes penicillin essentially the way Peoria did, by fermentation, by growing it, by harnessing the living thing rather than building the molecule. Sit with what that means. The German bet was not merely slower than the American bet. It was a bet on something that could not be done in time by anyone alive, a door that would not open for another 13 years, and that, once opened, led nowhere useful for mass production anyway. Germany was waiting for chemistry to rescue a problem that only biology could solve, and biology was precisely the tool Germany had spent decades declining to sharpen. The proudest chemical culture on Earth had staked its soldiers' lives on the one approach guaranteed to arrive too late. This is the real lesson buried inside the story of two dying soldiers, and it is not a lesson about who had the better scientists, because in raw talent the two sides were close to matched. It is a lesson about two different theories of how a nation should command the natural world. The German theory held that mastery means understanding, that you truly possess a thing only when you can take it apart and rebuild it to your own design, that control flows from complete knowledge. It is a noble theory, and it had built the greatest scientific tradition of its age. The American theory, at least as it played out in Peoria and Brooklyn, held something almost opposite, that you do not need to understand a thing completely in order to put it to work, that a living organism you cannot fully explain will still labor for you faithfully if you feed it, house it, and scale it up. That control can flow not from conquering nature, but from partnering with it. One theory produced elegant molecules and a dying soldier. The other produced a messy vat of mold and a soldier who kept his leg. Both were internally coherent. Both were the product of serious, brilliant people. Only one of them matched the actual nature of the thing they were fighting over, because penicillin was a gift from a living organism, and the way to have it in abundance was to accept that gift on the organism's terms rather than to insist on manufacturing it your own way. The American wager did something far larger than win a single wartime supply race. It opened an age. The very same fermentation approach that produced penicillin became the template for the flood of antibiotics that followed it, drugs grown from soil microbes in great steel tanks, and for much of the biological industry that shapes medicine to this day. Growing complex molecules inside living organisms, rather than assembling them atom by atom on a bench, turned out to be one of the central techniques of the modern world. Germany's deep instinct had not been wrong forever, only wrong for that one moment and that one molecule. But the moment happened to be the war, and the molecule happened to be the one that decided whether a wounded man lived or died. And in that moment, the fermentation tank beat the reaction vessel completely and without appeal. There is even a final, quiet irony that belongs at the very end. After the war, Germany was so short of penicillin, and Allied restrictions on German access to it were so tight, that German hospitals resorted to the same desperate measure the Oxford team had used on that first dying policeman back in 1941. They collected the urine of patients who had received penicillin and painstakingly extracted the drug back out of it to use again, a practice that continued in parts of Germany for years and consumed thousands of liters of collected urine. The nation that had invented the very idea of curing infection with chemistry the birthplace of the magic bullet itself, was reduced to reclaiming penicillin drop by drop from the bodies of the treated, because it still could not make enough of its own. Germany did not achieve true mass production of penicillin until around 1950, and when it finally did, it did so using American technology. At least one historian of the subject has raised the sharpest possible irony as a genuine possibility, suggesting that when the German leadership itself was treated with penicillin late in the war, the doses may have come from captured Allied stocks. It remains a hypothesis rather than a settled fact, but even the possibility captures how completely the situation had reversed. So picture the German soldier one last time, in the winter of 1943, as the fever takes him and the surgeon steps back with nothing left to try. He died surrounded by the achievements of the most advanced medical science of his age, in a country that had taught the world how to cure infection, killed by an infection that a pale yellow fluid a few hundred miles away was curing every single day. He was not betrayed by ignorance. His countrymen understood exactly what would have saved him. He was betrayed by an idea, the beautiful and mistaken idea that the way to own a medicine is to build it rather than to grow it. The Americans had quietly decided otherwise, in a laboratory meant for farmers, and that decision, more than any single battle, is why his side ran out of the one thing that could have kept him alive. He never knew the name of the thing that failed him, because it was not a weapon and not a general. It was a way of thinking, and by the time anyone fully understood that it had been wrong, the mold in the American tanks had already won. If this account gave you something to think about, a like and a subscribe help these stories reach the people who care about getting the history right.